In this lesson 3.7, we will focus on optimization. So we are going to be using the derivative to solve applied minimum and maximum problems. So we know that we can use the derivative to find absolute extrema on an interval, and we're going to be applying that to word problems. So for example, if we had a company and we had a function modeling our profits, we would want to be able to maximize that. On the other hand, if we were taking out loans to go to school, we would want to minimize how much we would have to pay back. So here are some general guidelines that we will follow as we work through these problems. We will draw pictures. If we can, we'll then introduce some variables. We'll figure out what it is that we want to optimize, which will either be to maximize or to minimize, and then we will find critical points and go on with using the first or the second derivative test to determine if we have maxes or mins. In our first example, we have a box that we are creating by cutting congruent squares from the corners of a 12 by 12 inch piece of cardboard. So first, we're starting with a 12 by 12 inch square piece of cardboard. So 12 is this entire side. It's also this entire side. All four sides of this are 12. And we are going to be cutting out congruent squares. So we're cutting little squares in here. So imagine if these green squares are cut out, you could then fold the flaps up to form an open top box. And we're asking, what is the most that box can hold? So we have our picture drawn. Let's introduce some variables. So the squares that we cut out, I'm going to call the sides of that x. So that side is x, that side is x, x and x, so on and so forth. So we've introduced some variables. Let's figure out what quantity do we want to optimize. They say, what is the most that the box can hold? We want to optimize the volume of this box. So I'm going to write an expression for the volume of this box. Generally speaking, volume is length times width times height. Keep in mind that when you fold up the box, these are the sides of the box that you're getting. So those would be the two sides because the green part's cut out. And then how tall the box would be x because that piece is folding up. So length times width times height. This orange piece right here, if remember the entire side was 12, we took away this x at the top, and we also cut away that x at the bottom. So that orange piece is 12 minus 2x, as well as this orange piece, because we have the same thing going on that other side. And then how tall the box is x. So the volume of the box is x multiplied by 12 minus 2x squared. Let's talk about some restrictions that we have on x. Considering that we're going to be cutting that out, it must be the case that x is greater than 0, or we wouldn't be cutting anything off of the sides of that piece of cardboard. And x also needs to be less than 6, because remember, the entire thing is 12, so if we cut 6 this way and 6 this way, then we don't have a box to work with anymore. So we want to optimize this volume. We want to maximize it more specifically because it says most. So we're going to be taking the derivative of this expression. In fact, I'll go ahead and multiply this out. I was going to do product rule, but I'll go ahead and multiply this out and use that to take the derivative. So we would need to FOIL this expression. So FOILing the 12 minus 2x squared is giving me 144 minus 48x plus 4x squared. I'll distribute that x and rearrange my terms, giving me 4x cubed minus 48x squared plus 144x. So that is our expression for volume. It is dependent on x. I will now differentiate the volume so that we can go and look for our critical values. So critical values are where the maximum could be happening. So to find our critical values, I'm going to take our derivative and I'm going to set it equal to 0. There is nowhere where this derivative does not exist. I can simplify this by coming in and dividing everything by 12. And then this is a quadratic equation that can be factored. Factors into x minus 6 and x minus 2, giving us critical values of 6 and positive 2. Now, when we talked about our restriction earlier, we said that x is not allowed to be 6. So I'm going to go ahead and cross that out. So the only critical value we have is x is equal to 2. Let's check and see if that is actually going to maximize the volume. And I'll do that by using the second derivative test. So I'm going to take v double prime, taking the derivative of this to give me 24x minus 96. And I'm going to plug our critical value of 2 into the second derivative. 24 times 2 minus 96 is a negative number. So because that is less than 0, we do know the graph is concave down at the critical value of 2, which does imply that we have a maximum volume when x is equal to 2 inches. So that's a part of our answer. That tells us, that answers this question: how large should the square cuts from each corner be to ensure that the box can hold as much as possible? They should be 2 inches long. The second part of the question is, what is the most that the box can hold? So to actually find the maximum volume, we are going to plug 2 into the expression for the volume. So we have, I'm plugging 2 in here. 4 times 2 cubed minus 48 times 2 squared plus 144 times 2 leaves me with 128, and this is cubic inches since we are talking about volume. In our second example, we want to find what point on the graph of y is equal to 2 square root x is closest to 8, 0. So just setting up a picture, I'm going to sketch a graph of the y is equal to 2 square root x function. It looks something like that. And let's say that the point 8, 0 is right there. So we are looking for some point xy on that graph that is closest to 8, 0. And what we want to do is we want to minimize the distance. Between these 2 points, xy, which we don't know what that point is, and 8, 0. So first, we have a picture. We know what variable, what expression it is we want to minimize. It is the distance. Let's write out what the distance is. I'm going to be using the distance formula. Generally speaking, the distance between 2 points, x1, y1, and x2, y2, is y2 minus y1 squared plus x2 minus x1 squared, all under the square root. That is just the distance formula. So the distance between these 2 points, I'm going to treat the xy as my second point. So that is x minus 8 all squared plus y minus 0 all squared, which is simply the square root of x minus 8 squared plus y squared. That is our distance. Now we want to minimize that, so we want to take the derivative of this distance expression and look for critical values and such. But the problem right now is that this distance has x and y showing up. But we do know that y is equal to 2 times the square root of x. So I can replace this y and rewrite this expression so that it only has x in it. So replacing y with 2 square root x will leave us with 4x because it is squared. So now we can proceed and take the derivative of this distance expression to help us get our critical values. So do remember that all of this is raised to the 1/2 power. So I'm going to be using the power rule and the chain rule. The new exponent on everything that was under the square root is going to be a negative 1/2. So I'm putting it all in the denominator Chain rule says I need to multiply by the derivative of the inside in my numerator. So I have 2 multiplied by x minus 8 plus 4. So everything in the numerator there is just the derivative of what was under there. Now that we have our derivative, we can look for when the derivative is equal to 0. That'll happen when the numerator of this expression is equal to 0. Solving this equation will give us that x is equal to 6. We also need to find where the derivative does not exist. That will happen where the denominator is equal to 0. This 8 minus x squared plus 4x being equal to 0. This is a quadratic expression. This is x squared minus 16x plus 64 plus 4x equals 0. I'll go ahead and combine like terms here. So this is really a minus 12x equals 0. And if I were to calculate the discriminant of this quadratic, b squared minus 4ac, I get something that is less than 0, which implies that that quadratic is never equal to 0. I'll just put never equals 0. So there is nowhere where the derivative does not exist. So the only critical value that we have is x is equal to 6. Now I'm going to use the second derivative test to ensure that that does maximize our volume. Alternatively, we could also use the first derivative test. So it really depends on whether or not right now you want to take the derivative of that expression, which you may not want to do, or if you want to use the first derivative test to evaluate that. Let's go ahead and use the first derivative test. That might be a little bit easier than taking the second derivative, which is very straightforward for us to do back here because we were only working with a polynomial. So here's our critical value of 6. I'm going to choose a test value of 5 and 7, and I'm going to be plugging them into the first derivative to see if I get something positive or if I get something negative. So I'm plugging them into this expression here. I don't have a calculator on hand, but I do know that everything in the denominator will always be positive because of that square root. And that 2 square roots, the answers of square roots always come out positive, and then we have a positive 2 in front of it. So if I were to plug 5 into the numerator, I would get a negative number. Let's see what happens if we were to plug 7 into the numerator. We would get a positive number. So we did go from decreasing to increasing. That does tell us that there is a minimum at x is equal to 6, which is exactly what we want because we are trying to minimize the distance. So we know that the x value is 6 at the point that has the minimum distance. And to get the y value, I'm just going to plug x into what y is equal to get 2 root 6 as our final answer there. In our final example, we have that Jonathan wants to draw a rectangle that is inscribed in a semicircle of radius 9. I'm going to begin to set this up, and to help with getting some perspective on things, I'm going to center the semicircle at the origin. It has a radius of 9, and here is the rectangle that he wants to inscribe on the inside of it. Notice that one side of the rectangle is on the semicircle's diameter. We want to maximize the area of this. So essentially what I want to know is if I knew the point where this was hitting the semicircle, xy, then this horizontal distance here would be x, this vertical distance here would be y, and I would have the dimensions, and then I could find the largest area. So generally speaking, the area of the rectangle is 2xy, and I say 2x because there is this whole other side here, x. Now let's talk about how we can rewrite that so that we can optimize this area. The equation of that semicircle is, well, generally speaking, the equation of the whole circle with radius 9 would be x squared plus y squared is equal to 81. So we only have the top half, so solving for y and taking the positive square root gives us 81 minus x squared. So I'm going to replace the y with the square root of 81 minus x squared. And now I'm going to use product rule to differentiate this area. So we have f prime g plus g prime multiplied by f. So simplifying this a bit gives us 2 multiplied by the square root of 81 minus x squared minus 4x squared over 2 square root of 81 minus x squared. I will simplify to get 2 multiplied by the square root of 81 minus x squared minus 2x squared over the square root of 81 minus x squared. Let's briefly talk about the conditions of x. Remember that the semicircle has a radius of 9, so this goes out to the point 90. So we definitely have the condition that x must be larger than 0 but smaller than 9. Let's go look for where our derivative is equal to 0. So I would set this entire equation equal to 0. I'm going to add that 2x squared over the square root of 81 minus x squared to the other side of the equation. Notice that I can get rid of the 2's, just divide both sides by 2. I will then multiply both sides of this equation by the square root of 81 minus x squared to get it out of that denominator, which leaves me with 81 minus x squared is equal to x squared. I will add x squared to both sides of the equation. Dividing both sides by 2 gives us x squared is equal to 81 over 2, and then I'll take the square root of both sides to get that x is equal to 9 over root 2. You could rationalize that to 9 root 2 over 2. At this point, we then need to verify that this is in fact giving us a maximum for the area. There's a couple of ways we could do that. We could take this expression here for the area, and we could then differentiate it in order to get a double prime. And we could check that a double prime of 9 root 2 over 2 is less than 0 in order for that to be a maximum. Or we could use the first derivative test and see that we see a sign change. I'm going to use the first derivative test. Here is our test value. I'll just put 9 over root 2 here. To the left of that as a test value, I will use 1, and to the right of that, I'm going to get an approximation for 9 divided by the square root of 2. It's about 6.36. You do want to make sure that you're not using a number that is bigger than 9 on the other side, because we do have that condition there. And we're going to be plugging 1 and 7 into the first derivative. You could use a table on Desmos, or you could use your graphing calculator. What's really important here is you're looking for the sign. What is a prime of 1 and what is a prime of 7? So when we plug 1 into the first derivative, we do get out a negative number. And when we plug 7 into, no, we get out a positive number, excuse me. When we plug 1 into the first derivative, we get out a positive number. And when we plug 7 into the first derivative, we get out a negative number, implying that the function went from increasing to decreasing, so that there is in fact a maximum at x is equal to 9 over the square root of 2. Now that we know what x is equal to, we can go on to solve for y to find the largest area. So I'm just using this expression here, and I'm going to plug in what we have for x. It doesn't matter which version of it you plug in. I'll just use this one. So I have 81 minus 81 over 2 under that square root, which does give me the square root of 81 over 2 again. which is again equal to 9 root 2. So both the dimensions that maximize it are square dimensions when x is equal to 9 over root 2 and when y is equal to 9 over root 2. So then the largest area, I'll just calculate the area by multiplying those two together, will be 81 over 2. And this will be in units squared.